This isn't a good thing that we see up here on the slide. This is the collapse of a bridge in California that connects Phoenix with Los Angeles on Interstate 10. Now, you know that California is undergoing one of its worst droughts. This is a drought of historic proportions, and this bridge failed because it rained too much. I've juxtaposed the bridge collapse with the recommended detour routes by Caltrans and the Arizona Department of Transportation. Here's where the bridge is out. To get around this bridge failure requires you to go through places that don't even rate as the middle of nowhere. The trucking industry estimated that trucking alone, never mind passenger vehicles, that this bridge was costing them $2.5 million a day. So this is the kind of infrastructure failure that we don't consider a catastrophe. This isn't Hurricane Sandy. This is just failure of routine maintenance. This bridge was inspected, and people were like, okay, it looks good. They just failed to catch the scouring that would happen under fast flow conditions to the supports that hold this bridge up. But you might say that's kind of a rare, kind of an isolated incident. So I took a look at what's going over in Indiana. Sure enough, just a few days ago, they closed a bridge on Interstate 65 that connects Indianapolis with Chicago. Here, they were performing construction. The construction involved driving some piles. The piles pierced a clay layer that opened up the sand below to, guess what? Scouring. It's the exact same failure on the exact same infrastructure. So now that we have two incidents, one in my home institution, one in my former institution, guess what? We have another detour map. This is what we call adaptation. It's not quite as bad. At least there's cornfields to drive through in Indiana, but the detour is, I can't say equally as expensive because I don't know. I-65 is a lot more congested than I-10 is, but the detour isn't quite as long. And the closure is, they say, indefinite. I'm a professor and I'm accustomed to grades. My peers in the American Society of Civil Engineers have graded our infrastructure. You can see the bridges are actually in good shape relative to our airports and to our levees and to other categories of infrastructure. Now in my class, if a student earns a D+, they're allowed to take the class over again, give it another try, get a B or something better on their transcript. We don't get a do-over in the world of our real infrastructure, and our funding level right now is about half of the $3.6 trillion over the next 5 years that they say would be required. The White House recognizes the issue. This is 2013, the same year that the latest infrastructure report card came out. And the presidential policy directives says it calls for a national unity of effort to strengthen and maintain secure, functioning, resilient, critical infrastructure. Sure enough, the national academies recognize this. We have our report from the National Research Council, Disaster Resilience, to help us along in this direction. Let's take a look at some of the recommendations of the report. Remember that the report is trying to advance us towards a more resilient approach. And why do we need a more resilient approach? Because the failures that we're seeing are, at the funding levels we have right now, inevitable. We need to understand how to fail and how to adapt to these failures. But when you examine the recommendation, it turns out that the recommendations repeatedly come back to this idea of risk. So it's risk management, it's risk reduction, it's risk-based strategies, and it's we need more quantitative risk models. Well, if we're trying to do resilience, the question here is, why are we spending so much time talking about risk? Because I remember risk. I remember it from the 80s, and I remember it from the 90s. And in environmental engineering, risk analysis begins with hazard identification. But we tried that with our bridges. We inspected the bridges. We looked for the hazards. We know the modes of failure, and we missed it. The reason that we need resilience is because risk is inadequate to deal with the complex systems that we are now facing. If we knew what the hazards were, then a risk-based approach would be fine. Because we don't know what the hazards are, we need resilience. So I want to try and convince you what I think the challenges are. And I've broken them out into these four. They're not independent, so these are overlapping challenges. The first one is we don't really know what resilience is. We certainly don't know what resilient infrastructure is. We have kind of a conceptual, a qualitative understanding. We need to sharpen that. The second is that the interdependence of these infrastructure systems makes it very difficult for us to understand how they operate. We have experts in bridges, we have experts in hydrology, we have experts in water distribution systems. What we don't know is how these things interact with one another. We need to know that better. The third is that even where we do, even where the risk analytic tools and that risk paradigm suits us well, we don't have the incentives or the governance structures to apply it. And the fourth is this really difficult problem of socio-technical integration. And here is where I'm focusing my effort and I'm the most ignorant. I've dived into the area of resilient infrastructure where I am least qualified. The question is, who among us is more qualified? And the answer is, I don't know. None of us have degrees or PhDs in resilience, at least not right now. What we need are people who are willing to go into the areas where they don't know how to operate and try to figure it out. So I'll show you what I think the approach that might help us out is. The first one is the problem lack of understanding what constitutes resilience. And what I propose is that we attempt to create this synthetic, this integrated, multidisciplinary view of what resilience is. So if we look at the way resilience has moved through our scholarly literature, we find that it dates back at least to the 16th century, and it's found with different understandings in different disciplines. I've labeled engineering, which we also heard about this morning, the resilience of a material, but there's psychology. There's resilience in the business world. Resilient supply chain is one that can weather shocks or disruptions and still deliver goods. There's resilience in ecology and the natural sciences. Over in the lower right-hand corner here, I've labeled disaster risk reduction, because this is a new way of thinking about resilience, and it should be inclusive of all of these other ways. We certainly need to think about resilient people. The evacuation buses don't drive themselves, for example. We need to think about resilient materials, resilient components, resilient engineering systems. We also need to think about resilient business models, and we need to be in harmony with the ecological systems in which we're embedded. So how do we do that? It turns out that words don't mean just one thing. What I've got here is a Google Ngram analysis. It shows the frequency of a word in the English language, that's the y-axis, over time. This graph dates from 1800 all the way up to the year 2000. And Ngram allows me to identify use of the word risk, both as a noun and as a verb. And we've almost forgotten that risk can be a verb as well. The light is turning yellow. Should I risk it and go through the intersection? So risk is something that we do, not just something that we have. But sure enough, in the late 60s, early 70s, we can see a big increase in the written English language of the use of the word risk as a noun, whereas use of the word risk as a verb remained flat. This is what I call the objectification of risk. It's sort of the scientification of risk. We start to think of risk as a property of a system that can be objectively quantified, and less as this behavioral property of something that we do. Keep that in mind, that words and our understanding of them change, but that in risk we have both this noun sense and this verb sense. Because I want to propose to you that if we're going to create this fundamental understanding of resilience that permeates all these disciplines, we need to think of resilience more as something that we do and not so much something that we have. We talk about resilience as an ability. An ability is something that you perform, ability to recover, ability to adapt. Ability is something that you do, it's like a verb, it's not just something that you have. So there's a dual understanding of resilience, and if we get too much wrapped up in our heads about risk, we'll think of resilience as a noun, when I'm proposing that we should think of it as a verb. Resilience is performed, not possessed. So what are the processes that must be performed to be resilient? And we've identified at least 4. Sensing. We need to understand the conditions in the environment around us. Anticipation. We need to be able to project those conditions into the future. That is, anticipate what the possibility spaces in the future are. We need to adapt to try and call forward to create the future that we want. And of course, we need to learn both from the past and learn as we go. These 4 processes are essential for a resilient system. You might have a robust system. You might have taller walls, thicker structures, better piles. That's not the same as a resilient system. If it cannot perform these 4 processes, I'm saying it won't be resilient. Here's the second challenge I said was the interdependence of complex infrastructure systems obscures our understanding. We don't really understand how they're interdependent, and what we need to do is decode those system interdependencies. This is a shot from 2005. This is Toronto. Now, when you design a culvert, a hydrologic structure, you understand that there's a probabilistic, I got my 100-year storm, but there's going to be a probability of failure within the lifetime of the culvert. We can't over-design these things to the point where we actually have 99% confidence that they won't fail during their lifetime. So we accept that we're limited in that way. But in this case, what the city didn't understand is the way the culvert that carries Black Creek below Finch Ave protected all of the other essential infrastructure systems. Underneath Finch Ave, we have water distribution, we have sewage collection, we have fiber optic cables. It turned out the main line into Toronto went right under Finch Ave. We have natural gas, and of course we have electricity. So now we see that there's this geographic interdependence. All of these infrastructure systems, they occupy the same place. And the road wasn't just for carrying cars. Turns out the road was for protecting all of these other essential infrastructure systems. That the culvert performed a critical role that nobody recognized. Now that we've seen this failure, we could go and examine all the other culverts and say, what are the interdependencies that we didn't understand? Taking a little bit different approach. Now here's a systems diagram of model as a dynamic system. This is an influence diagram of a problem that we see in the western United States. We're expecting warmer temperatures. How do warmer temperatures impact our power systems? Well, one of the things that warmer temperatures do, for example, is require more cooling in the city of Phoenix. This makes sense. Well, what do we cool with? Well, of course, we cool with electricity. One of the things that warmer temperatures do is reduce power plant efficiency, because these power plants depend upon evaporative cooling. And the hotter the water that runs through the evaporative coolers, and the hotter the temperature is, the less thermodynamically efficient, the lower the Carnot efficiency of the thermal plant. Which, if that's okay, we'll use hydropower. But one of the things that the warmer temperatures do is they reduce the stream flows that generate hydropower. We say, well, that's okay, we'll bring electricity in from other areas. But one of the things that the warmer temperatures do is increase fire activity that interferes with the transmission of electricity. So now we're beginning to see this positive feedback loop. When we have the cooling crisis, we will also have the greatest risk of fire, the least hydroelectric power, and the least efficient evaporative cooling plant generation. All of this is like a massive conspiracy to create a cooling failure, an electricity failure in the city of Phoenix. Now, how does that work out for you when your air conditioning goes out at 127 degrees? People die. Okay, what's the third barrier? I said we don't have the incentive structures even when we do understand the problem. How often do offshore oil wells fail? How often should we be expecting a blowout? This shows from 1965 to 1995, and you tell me, this is the number of wells, and then the straight line is the number of blowouts. Sorry, the frequency of blowouts per 100. Do you see a trend? I don't see a trend. I mean, you'd have to be an optimist to say, oh, look at how much better it's getting recently. What this is telling us is that even as the safety procedures and the technologies and the sensing technologies have improved over these decades, the risks that we accept have gone up. We've gone to deeper waters, we've gone to more difficult geological conditions, and the frequency of blowouts has remained about the same. It was a matter of time before we experienced the deep water horizon. We know there are blowouts. We know that our response to these blowouts is extraordinarily difficult, and we do not have reliable mechanisms of responding. If you remember this time, as I do, the way that BP was trying to cap the well became fodder for late night comedy. Think about the techniques that they were testing experimentally. Do you remember the top hat? If you don't remember the top hat, you might remember the junk shot. I mean, they were coming up with these sort of comical ideas about, we're going to stuff tires and golf balls and chewing gum in there. We're going to see if we can plug the well up that way. Anything goes. When nothing is working, you're going to try whatever you can while they drill a bypass well, which takes a lot of time. What I'm saying is, even when we understand where the hazard lies, and we have the tools to identify it, what we don't have are the governance structures or the incentives to prepare properly for when that inevitable failure comes. This is because we have different understandings of how resilience, sustainability, what our values and our objectives are. So I've mapped this out. I call this the sustainability spectrum to try and show us how sustainability and resilience fit together, and to try and help people who are concerned about these issues talk to one another. There are 4 different mindsets, and they're all overlapping, that I want to introduce you to. The first one is security. In ecology, security is a matter of these individual survival strategies. But we know that what constitutes survival at the level of an individual, what might be resilient for an individual, is not necessarily good for the herd. That individual sacrifice might lead to this greater group resilience. So scale is important here. Then we have reliability. We could, for example, ensure that there was never another commercial jetliner crash in the United States ever. And we would do this by simply not flying planes. But that's not the engineering approach. This might be more the security approach. The engineering approach says we care about how long it takes to get through the TSA check line. We care about how many planes are in the air. We care about moving people around. And we are willing to accept some risks to get better performance. So the reliability perspective says it's about this value proposition. It's the ratio. We want to keep things going, so we'll do failure and risk analysis and quality management. But resilience says things are going to fail. Whereas reliability says, no, we'll anticipate that, we'll guard against it. Resilience says we don't know everything. Resilience says we are ignorant. When things fail, we have to bring them back as quickly as we can. So here, we admit a temporary loss of function, but we're working towards a rapid recovery from those injuries. Lastly, the renewal mindset says tear it all down, build it all back up. This is the creative destruction, the innovation that says, never mind that failure might happen accidentally. If it's not broken, break it. These people are difficult to connect in conversation because they have different perspectives on what they're trying to do in the world. Maintain the status quo, disrupt the status quo. Great, the last one is socio-technical integration. And I'll go through this one with an example. These are the pipelines that supply gasoline to the city of Phoenix. It comes from the West Coast, Los Angeles, and it comes from the Gulf Coast in Houston. There are two. Now, imagine a scenario where one of them is down for planned maintenance and the other one has an unplanned interruption. What happens to the gasoline supply in the city of Phoenix? It's off. You must now run your city on storage. And this is okay. We have plenty of storage in the city of Phoenix. We can complete the maintenance on this pipeline. We can build a bypass for that pipeline. The city's going to be fine. But as soon as you publish the story saying one pipeline's down for maintenance and the other just experienced an unplanned breakage, what do the agents within your city, what do the drivers do? They hoard. And so now you have this social response, not to a real threat, but to the perception of a threat. So this is exactly what happened in 2003. You had these long gas lines. It was like going back to the 70s, but only for the city of Phoenix, because people were afraid. Not because there was a shortage, they were afraid that they were going to experience a shortage. So the pipeline company that owns the pipeline between Tucson and Phoenix, where it broke, they announced that they were building a bypass line and that the bypass line would be completed on such and such a date. People relaxed because now the confidence was restored that the bypass would carry the gasoline. Turns out that it takes like 4 days to fill this pipeline up. There would not be a drop of gasoline that comes through the bypass for 4 days until after it was completed. But it wasn't the supply of gasoline that was important, it was the perception of a shortage. So we have the technical, but we also have the social behavioral element that can create a crisis. We're going through, as I mentioned earlier, one of the worst droughts in California history. Here's a drought map from the summer of 2014. And this is a picture of the water main break that spilled 20 million gallons into the UCLA campus in the city of Los Angeles. The irony is that LA had just announced, Jerry Brown has made statewide water conservation mandatory now, but LA had just announced their own water conservation measures. You can't water your lawn and you can't wash your car. But spilling 20 million gallons off your roadway and into the UCLA basketball court, evidently that's another matter. So I want to use this to show the technical here and the social response. What happened a month later? Turns out that these water main breaks are happening all over Los Angeles. Evidently, the only way you can clean your car in Los Angeles now is you wait for a water main break, you get a sponge, you drive out there, and you're like, good, every once a month I can wash my car. The public response to this was outrage. How dare you curtail my water use when you are so carelessly maintaining your own? And the LA Water District said, not to worry. You know, we are highly competent engineers. We have a spreadsheet for this. And that spreadsheet has optimized a plan. Over the next 300 years, we will be, wait a minute, what? 300, they said it is cheaper to wait for the breaks and fix them than it is to go tear up all the roads, anticipate where the breaks are, and replace the pipes ahead of time. What do you think the social response is? Outrage. Now, the LA Water District is not sort of standing by this 300-year plan. We could say, look, it was pretty bad messaging. But messaging is exactly what's important when you're looking at this socio-technical integration. The fact is that we have institutions, and institutions are also part of our infrastructure. We can't point at the physicality of them, but these institutions operate under certain rules and norms. And one of the rules and norms in the LA Water District is you get a spreadsheet out, you compute the minimum net present value of whatever the maintenance and replacement program is. That's the basis on which you make decisions. But that doesn't serve the needs of the community, because inside their spreadsheet, they were only looking at their costs. They weren't looking at congestion. They weren't looking at spilled water during an acute drought. They weren't looking at costs that exist outside their agency. So in order to understand the socio-technical integration, we need to understand the institutions, how they operate, and the way that people respond. One more thing that I said that if I'm not careful, this talk's going to be a bit of a downer, because it seems like everything's falling apart. Can't we find the positive case studies? Can't we find the near misses? Can't we find the catastrophes that weren't? And study the people who adapted successfully? Well, here's one in front of our face, but it goes back to 1927. I'm going to take you from 1927 up to 2011 in the Mississippi River. This was one of the worst catastrophes of the modern U.S. history. It changed the way we think about civil engineering. It changed the way we think about the role of the federal government. It's been documented in this book, which I love, The Rising Tide. It resulted in federal legislation that empowered the Army Corps to tame the Mississippi River. And how are they going to do that? Like all good engineers, with infrastructure, levees, walls, all of which amounted to nothing in 1993 when the whole flood repeated itself. Where did all that investment go? Where did all that protection go? What did we get for our decades of effort at taming the Mississippi River? Well, it wasn't just the hard infrastructure that was built into the congressional legislation. There was also this adaptive option. And in 2011, we now had record in-stream flow. So this is a bigger amount of water than had ever been experienced in the Mississippi River before, but this is what the flood looked like. And how is it that 1993, with less water, was terrible, but 2011 was okay? The difference was the New Madrid floodway. The New Madrid floodway, which was created by Congress, put a flood easement on all the property here in eastern Missouri. To activate the floodway, you blow up the levees. And by blow up, I mean with dynamite. I mean, that's like what the Army does, right? You allow the waters of the Mississippi River to inundate the floodway, thereby reducing the pressure both upstream and throughout this stretch of the river, as well as downstream, because you smooth out the crest of the river. Then you got to blow it up again in a couple other places once the river gets below the water that is impounded to let the water back out. This is the adaptive response. And the Army Corps had never activated the New Madrid floodway in the entire history of managing the Mississippi River until 2011. As soon as they announced that they were going to activate it, what do you think the residents of the floodway did? Yes, they did. The argument was that even though that legal right existed, in practice, it was disallowable. Because these people are going to suffer. You can see what happened in the New Madrid floodway. Their farms, their homes, their roads, they all suffered, and they hadn't suffered in the 1993 floods. They thought, despite what was on their deed, that they would be protected to some extent. And here, we intentionally created a failure at one scale within the system in order to protect the larger system. Resilience exists in many scales. It could be the individual, it could be the group, it could be the community, it could be the nation. This raises a really critical ethical issue for resilient infrastructure systems. Up until now, we've been able to say, oh, act of God. That kind of stinks for these people that were in the way of the hurricane or the flood or the whatever. I know that, it's disproportionately, it's the poor people that suffer the worst, but I can't tell the hurricane where to go. In this case, we directed the flood. We created a mode of failure that was less catastrophic, but still caused suffering. This is the change in mentality that I want to leave you with. We need to move from this idea of fail-safe, that our systems will never fail, to understanding the modes of failure and make those failures safer. So this is from fail-safe to safe-fail. We need to move from reduction to embracing this incompleteness. There's some things I know. And as a scientist, I like to draw reliable conclusions within my boundaries of expertise. Now, as I mentioned before, I need to be able to work outside my expertise in the areas in which I'm ignorant and work with my best guesses. We need to move from definition to ambiguity. We'd love to have a definition of resilience that we can all agree on. It's not going to happen. We're going to have to embrace this pluralistic idea, this sort of poetic idea of what a term like resilience means. So when I tell my students, look, to operate in today's complex environment, you future civil engineers, you're going to have to get comfortable with ambiguity. They say, okay, Professor Seeger, we're ready to get comfortable. How are we going to be graded on ambiguity? A whole profession is not getting it. It's partly the way that we train our students to find the one right answer. In complex systems, there is no one right answer. We need to move from specification, the idea that we can control what's going to happen, and design for emergence, those things that we want to allow to happen even if they're not elements of our design. We need to move from this idea of reliability, that things will always work, to recovery. How do we bring them up to speed when they aren't working? And we need to move from centralized systems, which were the hallmark of the Industrial Revolution, to these distributed systems, which are going to be the hallmark of the Information Revolution. Lastly, we need to move from probabilistic, which is where risk analysis resides, to possibilistic. It's no longer important what the probability of the event is, because we now know from experience that we confuse unlikely with impossible. We're very bad at estimating these long-tail, highly improbable events that turn out to be extraordinarily consequential. So now instead of, I'm not saying that we abandon risk analysis, but we need to complement it with this idea of anticipation that says, what's the possibility space, not the probability distribution.